the other organizers for putting together this very nice workshop. I must say I learn a lot. And I think it's nice to have these mixtures of communities. So I learn a lot about splines. My talk today is a little bit of an outlier in the sense that it's about copulas. So let me ask, who knows what are copulas? Okay. Okay. So I have to explain what are copulas. And actually, I'm a statistician, so I use actually splines and B-splines as a kind of tool for, you know, estimating things. And I will try to explain to you how this basically works. What's special when you want to do this for copulas. So I will take my time to introduce copulas, and I will only basically come to the point where I show you where you can use actually splines for the approximation. And then more or less all the other steps you have to do at another time point, because this will otherwise be too much. Okay, let me try to explain to you what are copulas and what I'm interested in when you look at copulas. So the setting that you have is that you have D univariate random variables, and you're interested in the dependence structure between these D components. So think, for example, in finance, you have a portfolio, and the X1 to XD are actually the components in your portfolio, and of course they're dependent. Or think in ecological terms or climate terms, you can think of X1 to be like the temperature, X2 to be like the amount of rain, etc. And you know that the climate, of course, these things are linked, and you would like to figure out the dependence. You would like to figure out, for example, if X1 and X2 are moving in the same direction, right? So what are we going to use for that? And for that, I need to introduce what is a copula. If you have D univariate random variables, they have a joint cumulative distribution function. They have a joint distribution function, which I will denote like this. So that's this probability, right? So that's the joint distribution function. And each of these univariate random variables, of course, have their own distribution, called as the marginal distribution. And I will denote that distribution of X1 to be F1, of XD to be FD, etc. And so this is just the definition. Now, there is a very famous theorem, which dates back, which is a theorem due to Sklar in 1959, that basically proves the following, that there exists always a function C, which is defined on the D-dimensional hypercube and taking values in 0, 1, which is such that it's basically this function C couples the joint distribution function with the marginal distribution functions. And the word couples, copula, comes from the Latin, which is this coupling. Now, this function C is special in the sense that, so it always exists. It's not always unique, but it is unique when you have that these marginal distribution functions are continuous. So I will, for the rest of the talk, always assume that they are continuous, right? And what is extremely important is that that function C actually fully characterizes the dependence between the components. So you basically, it's like you decompose your joint distribution function in the dependent structure and in the marginal distributions. Okay, next slide. I can also write this in a different way. So this is Sklar's theorem. If I now do, I call this argument U1, this argument UD, then I can basically write it from whatever side that is, for you from right to left, by using actually the inverses of these functions. So these are like the quantiles, if you, it's the inverse of the function fg. If you write it like that, so this is just writing it the other way around, I write it again with probabilities. I apply F1 on each side here. I apply F2 on each side here, Fd on each side here. Then you end up with this probability, and you see that you end up with actually a transformed random variables. X1 is transformed by its own cumulative distribution function. Fd is transformed by its own cumulative distribution function. And there is one of the basic, first things that you learn in first year probability course is the integral probability transform, which tells me that if you take a random variable and you transform it by its own cumulative distribution function, then this resulting uj, as I call it, is always uniform distributed on 0, 1. Which means that if I now write this back using these uj notations, you see that the copula is actually nothing else than a multivariate distribution function, but with uniform marginals. And there is a dependent structure between these, right? And that is this C. Okay, so that's the object that I would like to estimate. Any questions so far? Yes?
Could we check if there is another microphone to turn off so that you can...
Yeah, I was actually, I don't know.
Well, there's a second microphone. Maybe just add a head microphone.
Oops. No, I don't see anything switched on. That one. Ah. Pardon?
Your scalar theorem is the same as holomorphic representation theorem. No?
I have to check that. Yeah, but yeah. Okay, so let me give you an example. Let me. Pardon? Okay, let me give you some example if it's not clear yet. So basically, I just go to a bivariate case, and I know that the joint distribution function of this bivariate case is actually determined completely by the copula and the marginal distributions. And I take an example, example 1 and 2, where I take the same copula structure, a Clayton copula. If that says something to you, I'll show you a picture afterwards. But I take different marginals, I take different marginals, right? The first example, I take the marginals to be a normal distribution. The first marginal, the second marginal exponential, and in the second example, x1 is exponential 2, and this is a beta distribution, any kind of distribution. And what I'll show you on the next slide is I'll show you a sample, I think for size 700 and 400, but doesn't matter too much, for each of these examples. And that gives you this kind of picture. So this is x1, x2 for the first example. This is x1, x2 for the second example. And if you see that and ask you the questions, do you have an idea about the dependent structure? There's not much you can say. If I would ask you the question, is it the same dependent structure or not? I think it's hard to tell. But actually, they do have the same dependent structure, and that you see when you basically apply to the data this F1, which I know because it's a simulated example, to an F2 to the other part. And then you get U1, U2, U1, U2 for example 1 and for example 2. And there you basically see that the dependent structure is clearly, the same for these two underlying data. And this is this dependent structure. That's this copula, which I used in this example. So which lives on 0, 1, which lives on 0, 1, and which is just a bivariate cumulative distribution function, which has uniform marginals. That's it. Now, a copula is something which has been studied a lot. There are nice books about it. And of course, what is important is that you know some of the properties. So first of all, I know that if I have at least one of these arguments which is equal to 0, then this is equal to 0. Yeah. If you have all arguments 1 except for UK, so at the kth position, then you get UK, right? Because you have uniform marginals. And of course, what I also need to have is that if I have an area in the hypercube of dimension d, then of course it needs to be such that it gets positive probability. A probability cannot be negative, right? And that you can express in this general way, but let me show you a picture in the two-dimensional case. So this is the unit square. I have this blue area here. And what is the probability given to that blue area through the copula, of course? Well, that is just obtained by taking the values that you have here, minus the values that you have here, minus the values that you have over that, plus the value that you have over there. And that's this expression. And that needs to be bigger or equal to 0 for any kind of rectangle that you take, right? So this is in the bivariate case, but of course you have in a multivariate case what I showed you here. There are other nice properties, and by the way, there are quite a lot of books on copulas. A copula function can be shown is always Lipschitz continuous. So it's always continuous. That's important. And another important fact is that if I take T1 to TD increasing transformations, and I apply that to my random variables, so you get a new set, a transform set of random variables, then they have the same copula. That's important, yeah, which is also logically, it should not change the dependence. There are many other properties, but these are the ones that I basically will encounter later on. Now, what about the following? If the dth order partial derivative of that copula exists, then you call that the copula density, right? And since we have this expression by Sklar's theorem, and if the dth order partial derivative exists, I take it from this side, I take it at this side, and you get this. So the joint density function of x1 to xd is expressed in terms of the copula density, and there is also the product of the marginal densities coming in here because of the chain rule, right? And last important remark is, what if I have independence? How does that copula function look like? Well, if you have independence, then the copula function is just the product of all the arguments. And the density and the copula density is 1. So you know very well which copula basically characterizes independence, which is also crucial. Let me give you an example, if you still need it. Let's say yes. You all know bivariate normal distributions, right? Bivariate Gaussian distributions, the nice bell-shaped one-dimensional distribution, or in 2 dimensions you also have it. So if we have x1, x2, a bivariate normal distribution with mean mu1, mu2, so vector mu, and you have a variance-covariance matrix, a 2x2 matrix, which gives you on the diagonal the variances and which gives you off diagonal the covariance between x1 and x2. Then we know, again, basic course in first year probability, I hope, that x1 and x2 are always univariate Gaussian or normal also, right? In contrast, you can have a Gaussian copula and combine it with any kind of marginals that you want. It's not a bivariate Gaussian distribution. It's something else. You take the Gaussian dependent structure and you put any marginals you want. I give you an example. Now, what is a Gaussian copula? Just going back to what I did before, a copula is nothing else than the joint distribution function of these uniformized marginals, right? So here, a Gaussian copula is nothing else than you take the cumulative distribution function of a bivariate normal with this variance-covariance structure, and you apply it in these quantiles, univariate quantiles, right? Now, since there is this property about this transformation, you can always, this is actually equal when you work with the correlation matrix, which is easier. And the correlation matrix depends on correlation coefficient, If it's 0, we have independence. We heard that, I think, from John. If it's away from 0, then you have some kind of dependence. Now you can use this with any kind of univariate distribution, and I'll just show you one example where I took for the marginal one a standard normal, and for the other one a chi-squared 1 distribution. Yeah? Actually, a sample from that bivariate distribution that results from that is shown over here. When I apply, F1 and F2 to it, so I uniformize these margins, I get U1, U2, and this is actually the dependent structure, which is dictated by this Gaussian copula. What do I show here? Well, this is a picture of the joint density of X1, X2. It's far from a normal, right? And this is actually a picture of the copula density. When you take this, the Gaussian copula density. And these are basically the objects that we would like to estimate, without that we know the form of them, right? Okay, any questions so far? Ooh. This was my introduction to copulas, so I hope you all capture what copulas are. Now, let's do statistics, because now I start feeling a bit, well, no, not necessarily. But so this is my vector of my D univariate random variables, and I want to figure out the dependence between those, right? Using this copula characterization. I do have a sample from that. A statistician can do nothing without data, right? So, well, we can do probability theory. So this is the sample, IID sample from X, which I denote like that, or you can think of X1 as being this, and Xn as being this. So n is a sample size. So Xji, the first index refers to the component, and the second index refers to which observation I have, right? And what's the aim? The aim is, as I said before, we want to estimate the copula C and its density if it exists, of course. Now, a first issue that you have to realize is that I do not have observations of these uniform marginals. I don't have observations from that. If you would have observations from that, it would be easier in some sense. So that's the first thing to realize. A second thing to realize is when you do statistical inference, if you would tell me, okay, you have a Gaussian copula with rho is equal to 0.8, I know the copula fully. If you tell me you have a Gaussian copula, but I don't know what rho is, then this is like a parametric form for the copula. If you tell me the marginals are normal and I don't know what the variance is, then this is parametric, etc. But I put myself in the situation which is actually the most realistic situation if you come to data applications, which is that I don't know anything about the marginal distributions, except that I'm assuming that they're continuous, right? I don't know anything about the copula, at least in the next 4 to 5 slides, I think. I don't know anything about the copula. I will go a little bit not to parametric copulas, but with something which is in between, namely large classes of copulas which are there, where there is still some unknown function that I would like to estimate, right? Okay, so let's start with the situation that you don't know the copula, not at all. Okay, well, so remember that the copula is nothing else than the joint distribution of these uniformized marginals, right? If I would have a sample of these uniformized marginals, then estimating this probability distribution is not, you can do this with the empirical version, right? So the I is the indicator function. I could do that, and I'm done. You don't have a sample from U1 to UD. If I would know F, if I would know all the marginals fully, then I could do the same. I could use that information to basically transform each of the data points using these known marginal distributions to get actually realizations for these U1 to UD. But also that's not realistic. What is realistic is that I don't know these marginals, not at all. But that's not a problem because I can estimate them non-parametrically. How am I estimating Fj, which is the cumulative distribution function, or which is the distribution function in short, of xj? Well, you take all the observations that you have in xj and you build a uniform estimator for that. So you take the empirical estimator, which I denote by a hat. And then I can, of course, get pseudo observations, right? Because I apply these estimators as this estimated transformation to the data. And I get not realizations of U1 to UD, but something which is close to it, right? And then a first estimator for the copula is basically that you use these pseudo observations here. And that's actually the empirical copula, which was among the first estimators that was proposed by the late Paul de Heuvels. He passed away last year. But this empirical copula is studied a lot. And it's the simplest things that you can think of. But in fact, it's not a copula. Why not? Because it's a step function. It's not continuous. And that made that people, so this is the simplest non-parametric estimator, that made that we started working on that, and I mean the whole community who does this non-parametric copula estimation. And you can do a lot. You can do EPS, not that, this. You can do kernel methods, you can do transformation methods, you can do wavelet methods. I worked a lot in kernel methods. Some of my references are there. I didn't work on splines, by the way, but I thought it was good that you know how you can use splines and copulas, right? And I will start with how you can use B-splines in this fully non-parametric setting. And I will do that just going to the bivariate case. And I will start with Bernstein copula estimation. There are a couple of references here. By the way, if you want references, I can give you a lot. There are a few on the slides, but yeah, anyhow. Okay, Bernstein estimator of a copula and a copula density. Actually, it's very easy, and probably you can imagine it's easy because you have that the copula function, bivariate copula function, lives on the unit square, right? It takes values between 0 and 1. It's continuous. So I'm in this space of continuous functions on the unit square. So I can present C. I can approximate it by a Bernstein polynomial, which is here, right? Which is the approximation. So these are the Bernstein polynomials. I take them here to be of the same degree in the two dimensions if you want, but of course you can take it differently. And we know that these Bernstein polynomials, for somebody who knows, who's more in probability and statistics, these are actually the binomial probabilities. And we know, of course, this. Okay, so this is again the same expression. I have this. One thing before I move on is that it was shown actually that this is itself a copula, which means that you can check that easily, and that is due to these Bernstein polynomials, which are there. So if you take it in 1, 1, for example, you get 1. Now, the problem is, of course, you don't know C. And there, the statistician is there with his or her observations. And what do people do? Well, they replace the C here by the empirical copula, right? Which is a Cn. And this is actually the Bernstein estimator for the copula C. And this M acts like a smoothing parameter and things like that, right? Usually we take it to be, nowadays we take it to be equal to the sample size. The estimator for the copula density is easy because you just have to take the second order partial derivative with respect to U1 and U2, and you get this. So this ends up with the derivatives of these. So that's easy, right? So this is when you use Bernstein polynomials. Then people started using linear B-splines. I just drop a few references. I also learned here at the workshop that Tatjana did work on that. So, you know, I learn a lot. There is a saying, you're never too old to learn. I can assure that. And then there is some recent work where they have used B-splines of any kind of degree to estimate copula. It's actually fairly recent, right? And I'll just go over it reasonably quickly. And you give me a number of knot points, you choose a degree for the spline, and you come up with a B-spline basis of dimension m. Make sure the B-splines are normalized. They have to be densities, right? They have to be densities, and I consider the cumulative basis function, which means instead of going to 1 here, you go to u. It's like the CDF of that density, right? Okay, next. Then you have the bivariate B-spline copula, is this thing where you have all the coefficients, which you can stack in a matrix. We have seen that the previous days a couple of times. But of course, you need to request, this still has to be a copula, right? So you need to request that if you sum over all the rows of the matrix and all the columns of the matrix, and then afterwards you sum in the other dimension, this all should be equal to 1. And of course, they cannot be non-negative because a copula is a probability distribution. The density function is easy because then you take the derivative of that, which is actually that density which is in your basis. And of course, as I said, you need to satisfy all these conditions. That's what you have to do. Bernstein copula, Tom told that on Monday. I think that Bernstein is a special case of B-splines, right? So here it comes up again. You have that in the case of the Bernstein polynomial, this RKL is actually equal to that. Now, if you're not in the Bernstein copula setting, how are people estimating these coefficients from the data, satisfying these constraints, right? Because that's important. A way to do that, and I'm really not going into detail here, which is the way how it's done in this paper, is that remember that we have the joint, the bivariate joint density, which you can express in terms of the copula density, if it exists, of course, times the product of these marginals. Now, if I have a joint density, I can write down a likelihood, right? I can write down a likelihood, but don't forget that I don't have observations on these u's, but no problem. I use the u hats everywhere. If you take the logarithm of this, well, you take the product first and then you take the logarithm, then you see that these two terms basically do not depend on this matrix R. So you can drop these. And then you can try to do some kind of maximum likelihood. You can try to maximize this objective function over R with respect to the constraints. You can build in some penalization if you want, etc., etc. So that's the way how it's done here. I don't know how I am with time. By the way, this is actually the paper is only about the bivariate case. That's where it stands nowadays. Okay, let me quickly go to the case where you know something about the copula, but not much. And this is typically, so you have large classes of copula families. And the ones that I'm thinking about is, there are actually three important ones. There are multivariate Archimedean copulas, multivariate extreme value copulas, which are in particularly when you think about climate changes are used there. And you have multivariate elliptical copulas. For example, the Gaussian copula is an example of that. Student T copula is another one, etc. So these are last classes. What is very special in each of these last large classes is that actually it depends on an unknown function, univariate or multivariate, that you then have to estimate. That there is this additional structure that's important. And I'll just now, for this talk, just go to the second class, just to give you an idea of how you can do things, right? Or how things are done. Now, multivariate extreme value copulas, and maybe I'll just stick to the bivariate case. It looks like this, with a function a, which is defined on a unit interval and takes values between 0.5 and 1, and which is convex, and which is such that a of t is bounded by 1 and bounded by the maximum between 1 minus t and t. So that's that unknown function. Can be anything. There are zillions, well, a lot of extreme value copulas. And so when you want to estimate this copula, you have to estimate this a function, right? But you know that it satisfies these conditions. By the way, some examples, if a of t is equal to 1, you get the independent copula. When a of t is this function, and it depends on a parameter, then, which is one of the well-known extreme value copulas, and by the way, it's the only copula which is also an Archimedean copula, the only one. And you see here the function a, when I have the independence, when theta is actually equal to 1, and there are two other curves which gives you this a function for two other values of theta. And it's that a function that I want to estimate from the data using B-splines. Now, in the multivariate case, just quickly, what you end up with is a function a, but now it's a function defined on a Unix simplex in RD. So now you have to estimate a more dimensional function satisfying these constraints. So the problem is more difficult, and nobody has done use splines for that. Not yet. We are at the stage of bivariate. How do you do that in the bivariate case? In the bivariate case, well, if you think of the copula, if you take the logarithm on this side and you then bring that to the other side, you have this. Now this, what does it mean? If I call this t, then a of t should be equal to that, right? For any u1, u2. Now you have your data, right? You can calculate your pseudo observations, right? C I can replace by the empirical copula. And so I can effectively produce a kind of pseudo observations here, which are, this is pseudo observations for that, right? I call it TI. These are pseudo observations for that side. And then you basically use that scatter plot to fit the B-spline. But be careful, A has to satisfy these conditions. It's not so easy, right? Now, if you go to any of the other classes, yeah, so I should say that if you want to look more, look at these papers. It's not so easy to impose convexity, by the way. You have these constraints that you have on A is something which is really quite special in this case, in these cases, I should say. And anyhow, the message that I want to convey to you is that if you are in a certain specific class of copulas, then you really have to make sure that it's dealing with the constraints and how you can, at which moment you bring in the B-spline estimation, which is crucial and which is very different if you go to any of the other classes. Do I still have a few minutes? Okay, because I just want to mention, I mean, there are many topics that are there, which I didn't touch upon, but I think for this audience, well, they changed in the course of the week. Why? Because Niba was giving a talk, I don't know when, 2 days ago, 1 day ago, talking about B-splines when you have data on the circle, right? Now, when you have data on a circle, call it angles, θ1 to θd, you want to know what's the dependent structure between these. What's the dependent structure between the orientation of the wind and, for example, the position of a, of a wind farm somewhere? You can think of it like that. So your data now take values on a d-dimensional torus. You can write down what is the joint distribution function. You can apply Sklar's theorem, by the way. That's not a problem. you can apply it. You have to be a bit more careful that you enter always between minus pi and pi. That's why there are these things over here. And actually that copula is now defined on the d-dimensional torus. It's again a multivariate distribution function, but now for angular data with circular uniform, well, with uniform circular distributions, right? And you can, well, they have a name in the literature. Since this paper, they are called circulars. And actually, I contributed in that by doing some kernel estimation. I didn't do any, but now with Diba's ideas, maybe you can do some kind of B-splines there. That's one thing I want to mention. And maybe a last thing is that often when you have a dependent structure, you have covariates. Think of, for example, the dependence between temperature and the amount of rain. It can be different in different regions of the world, right? If you think of a portfolio, it can be different depending on the economic situation of the country where you are. So there is usually a whole bunch of covariates, which I now have just the univariate case Z. That's not a problem, because then you're interested in conditional dependencies. John has talked about conditional densities and distribution functions. So it's that. So now you apply Sklar's theorem to conditional probabilities. That's no problem. So you have something like a conditional copula, where actually the copula function itself depends on the realized value of the covariate. In which country are you? In which region of the world are you? Are you a female or a male, etc.? So all these, the dependent structure can change with the realized value of the covariate. Actually, there are Bernstein conditional copulas. It's just this, but now there is this C sitting there. So you can't use the empirical copula anymore. You have to do something else. People use kernel estimation there for replacing that. And this is one of the references. It's fairly recent, but I'll stop here. I have some other problems, but stop here. Thank you very much.